Sarah, during your talk, you have a few options as far as questions go. So I think we don't have crazy numbers of people anymore these days. So we'll probably just allow the audience to unmute themselves and ask a question if they want, if that's okay with you.
Yeah, that's perfectly fine with me.
Yeah. And as far as the chat goes, I'll sort of monitor it and ask questions from it from time to time, or feel free to look at it yourself if you like. It's or if you want to pause like every 5-10 minutes and solicit questions, you can do that.
Yeah, I can try to remember to do that, but I might forget, so people should unmute themselves if I forget to do that.
Cool.
Yeah. Can you see my mouse, by the way? On top of the slides?
Yeah, okay. You can use it as a pointer if you like.
Yeah.
Wait another 20 seconds or so.
Sure.
Right. So welcome, Sarah, and welcome back, everyone. It's been a pretty busy summer of conferences. So thanks for joining us for the Western Hemisphere Colloquium on Geometry and Physics. Before I introduce our speaker, everyone should be able to unmute themselves during the talk. So if you'd like to ask a question, feel free to just interrupt and do so, or write the question into the chat, and someone will pick it up. And we'll have about a 15-minute talk with the question and answer session at the end. It's a bit flexible. Right. Otherwise, we are extremely happy to have Sarah Harrison here from McGill University, and she'll be talking about new BPS algebras from superstring compactifications.
Okay. Thanks for the intro, Tudor, and thanks very much for the invitation to speak here today. So what I'm going to talk about today is mostly based on a recent paper that came out last week with the 3 co-authors, Natalie Paquette, Daniel Persson, and Roberto Volpato. And I'll also mention some earlier work with some of the same collaborators. And I'd also just like to note that some of my talk has some overlap with a talk at the series given by Natalie Paquette last October, but I hope to give you some updates from the time in which she talked about some similar things, as well as some review of what she already said in case you weren't there or don't remember things from 9 months ago. So the kind of connections I'm going to be talking about in my talk today are between these 3 areas of sort of physics and mathematics. The main objects of study are what are called Borcherds Kac-Moody algebras or superalgebras. So we'll see both of these things. And roughly speaking, these are infinite dimensional generalizations of Lie algebras. And they were first introduced by Borcherds in his proof of the monstrous moonshine conjectures relating the modular J function to representations of the monster group. And one of the main ways in which they're different from regular Lie algebras or Kac-Moody algebras are that the Cartan matrix can now have imaginary simple roots in the algebra. And so I'm going to be talking about sort of some connections between these BKM algebras and physics, in particular, the physics of BPS states and certain string theory compactifications, as well as objects in number theory, which are essentially automorphic forms of various types. So let me start with some very broad motivation about why we want to study these structures and the connections between them. So one kind of physical motivation is to better understand mathematically the symmetries which are underlying the structure of string theory. Now, this is a very broad question, one which you could attack in many different ways. And the specific setting we'll be looking at this question is in terms of very special compactifications of string theory with a lot of symmetry, where we can really compute a lot because there's supersymmetry and there's discrete symmetries as well. And another physical motivation is that BPS states in particular have played a very important role in the physics of quantum field theories and string dualities throughout the past several decades, and they've been observed in many different contexts to have interesting connections to things like geometry and algebraic structures in mathematics. And a third motivation I'll mention is the idea of moonshine, and I won't really focus on moonshine in the talk, but I'll mention some aspects of it somewhat briefly, which is a connection between finite groups and modular forms. And often these finite groups happen to be one of the sporadic simple groups. And one question you can ask is, what is really the natural objects which the sporadic simple groups act on, the natural physical objects they act on, and whether we can understand some of the beautiful mathematical properties of moonshine by studying particular physical setups. So I want to start by talking a little bit about what Borcherds Kac-Moody algebras are. And the way I'll introduce them is kind of by talking about the first example, which motivated Borcherds to develop these structures. And we can see some of their properties by beginning with this famous formula satisfied by the modular J function. So the J function is the unique modular function for SL2Z, which has the following Fourier expansion in e to the 2 pi I tau. It starts with Q inverse plus 0 times Q plus 196,884 times Q plus ... And it satisfies this beautiful identity that if you take the difference between J of sigma and J of tau, where sigma and tau live in the upper half plane, this difference can be written as a product where the powers in the exponential are these Fourier coefficients in the Fourier expansion of the J function. And the connection to moonshine started with the observation that this first coefficient in the Fourier expansion is 1 plus 196,883, which is the dimension of the smallest irreducible representation of the monster sporadic group. And so very briefly, Borcherds reinterpreted this formula here, which relates this difference of the J function to an infinite product as what's called the denominator formula for a particular infinite dimensional algebraic structure, which I'll call this frac M, which is known in the literature as the monster Lie algebra. And you can compare this with the familiar Weil denominator formula for Lie algebras, which relates a sum over the Weil group acting on roots of the algebra to an infinite product over positive roots of the Lie algebra. So here is an infinite product over roots in this structure M, which is related to a sum over this Weil group action on the left-hand side. So this, I mean, I haven't really proven to you that there exists an algebraic structure behind this formula, but there does, and this algebra is sort of the first example of a Borcherds Kac-Moody algebra, which is that infinite dimensional generalization of the Lie algebra that I mentioned earlier, which can have imaginary simple roots. And the connection between this algebraic structure and moonshine has to do with the fact that there's a natural action of the monster group on this algebra. So the motivation for Borcherds was monstrous moonshine, as I mentioned briefly earlier. So let me tell you a little bit more about that. So after the coefficients in the expansion of the J function were noted to have some kind of connection to the monster group, Conway and Norton made the following conjecture, which is that there exists some integer graded vector space, which is always referred to as V natural, which has a natural action of the modular group, so that each level in this grading is some kind of finite dimensional representation of the monster group. And if you take the trace over each level in this module, you precisely get the J function. And furthermore, there's a beautiful connection to the theory of automorphic forms by studying the so-called McKay-Thompson series, where instead of computing the trace of the identity element, you compute the trace with the insertion of an element in the monster group. And you get some kind of modular function, which are called McKay-Thompson series and are denoted by T sub G of tau. And these modular functions are modular under some kind of subgroup of SL2R, gamma sub G. And one of the interesting properties in monstrous moonshine is that these modular functions are precisely Haupt modules for genus 0 groups. So Haupt modules are just a map from the upper half plane mod this modular subgroup to the Riemann sphere, and the fact that H mod gamma has the topology of a sphere is what people mean when they say the group is genus 0. So in proving these conjectures of Conway and Norton led Borcherds to develop the concept of Borcherds Kac-Moody superalgebras. So a little bit more about this module V natural. A construction of this module was furnished by Frankel, Lepowski, and Merman using the structure of vertex operator algebras. And specifically, this module can be constructed by taking a theory of chiral bosons on a 24-dimensional torus given by R24 mod the Leech lattice, and then taking an additional Z2 orbifold of that. And that theory has partition function, which is precisely given by the J function, capital J. And that theory as well has a natural action of the monster group on it. And then in order to prove the monstrous moonshine conjectures, that involves a technique developed by Borcherds where one can construct a Lie algebra of physical states based on a particular sort of string theory inspired BRST reduction of a vertex algebra, which involves tensoring V natural with a lattice vertex operator algebra given by R2 mod gamma 1, 1, a unimodular lattice of signature 1, 1, tensored with what's called a ghost theory of ghost vertex operator algebra, which is very familiar to string theorists. And then once you compute the BRST reduction of this theory, you precisely construct a Lie algebra of physical states, which has a natural action of the monster group. And you can consider what are called twisted denominator identities, which involve considering this algebra structure where you twist by an element G of the monster group. And you find a series of identities which are similar to the identity for the J function that I presented at the beginning. And this leads you to prove the Haupt module property for all of these McKay-Thompson series. Now, I briefly want to mention some physical motivation as well for studying these kinds of algebras, besides the fact that it's a curiosity that seems to appear along the way of understanding monstrous moonshine. So I'm going to just briefly mention two specific examples of where hints of BKM algebras seem to appear in physics in the 90s, though there are a number of others that I don't mention here. And the first example has to do with studying black holes in type 2 string compactifications on K3 times T2. And there's a famous formula due to Dijkgraaf, Verlinde, and Verlinde for the degeneracies of black holes with charges, electric and magnetic charges, which are called capital P and Q. These black holes satisfy some amount of supersymmetry preserving, well, they preserve some amount of supersymmetry, which is called quarter BPS. And you can compute the degeneracies by taking a contour integral over this Siegel upper half plane of 1 over phi 10, where phi 10 is a particular weight 10 automorphic form, which depends on complex variables sigma and tau, which live in the upper half plane, as well as a complex number z. And if you do perform this contour integral correctly, you extract some coefficients in this automorphic form, which tell you the precise degeneracy, the number of black holes with electric and magnetic charge P and Q. And phi 10 is known to be the denominator function of a particular BKM superalgebra. And there's a proposal that was due to Chang and Verlinde that this algebra governs the physics of quarter BPS black holes in n=4 string theory, and tells you beyond just their degeneracies, information about physical decay processes between black holes with different charges. And a second example where hints of BKM algebras have appeared in string theory in the past comes from what are called threshold corrections in 4-dimensional n=2 string theory. So an example of a 4-dimensional n=2 theory is the compactification of a heterotic string on K3 times T2. And when you compactify string theory down to some dimension, like 4 dimensions, one thing you want to compute are terms in the effective space-time action. And in particular, you want to compute the coupling constants that appear in front of terms in your effective Lagrangian. And so many people did this in the mid-90s for particularly supersymmetric compactifications. And one example of such a coupling constant you can compute is the one-loop renormalization of the gauge coupling constant, which you can compute because it mainly contains contributions coming from particular BPS states in the theory. And what you find is that this contains a term that looks like log of j of it minus j of iu, where t and u are some moduli of the compactification. And this is precisely the additive side of the denominator formula for the monster-Lie algebra that we saw at the beginning of the talk. So this looks like the BKM algebra has some kind of relation to these BPS states, which are contributing to this coupling constant in the space-time action. And this particular observation, as well as similar observations in a number of other examples, led Harvey and Moore to propose that BPS states in string theory may form an algebraic structure, which could be a BKM algebra in particular, or some kind of generalization of it. And so we would like to explore this proposal, if we can, in other settings. And finally, I want to mention some previous work of my collaborators, which was probably discussed in the talk last fall by Natalie Paquette, so you can look there to see more information about this particular motivation. So they tried to physically reinterpret the results of Borchards, in particular the results that this monstrous Lie algebra he constructed leads to an understanding of the genus zero property of monstrous moonshine. And the way they do this is they consider a particular compactification of heterotic string theory down to 2 dimensions. This compactification involves taking some kind of asymmetric orbifold of the string on T8, such that the world sheet theory factorizes into a product where the left movers precisely form this holomorphic VOA given by V natural, and the right movers take the form of a super VOA, which is called VF natural, which I'll briefly describe a bit later in the talk. And they do a BRST reduction, which is similar to Borchards' original construction, to compute the space of physical BPS states in the 2-dimensional string theory. And they show that these physical BPS states form a module over the monster Lie algebra. And then they try to interpret the fact that the genus zero groups, gamma G, appearing in monstrous moonshine, they try to interpret them as some kind of duality groups in some closely related string theory compactifications called CHL models. So I'm not going to say too much more about that. But sort of the key question here is whether there are other contexts in string theory where we can construct explicit relations between Borcherds Kac-Moody algebras, BPS states, and perhaps dualities or duality groups. And if this can give us insight into the physical interpretation for other instances of moonshine beyond monstrous moonshine itself. So that brings me to a brief outline of my talk. So first, I'm going to discuss some other instances of BKM algebras and superalgebras beyond just the monster Lie algebra, as well as a brief description of their mathematical structure, including their denominator formulas and connections to automorphic forms. And then I'm going to talk about how we can interpret them as algebras acting on BPS states in very specific string theory models. And finally, end with some conclusions. So I'll ask briefly if there are any questions at this point before I go on.
I have a really embarrassing physics question.
Yeah, sure.
Since you invited it. So in the BPS black hole story,
yeah.
Where's the in that geometry, where is the torus or the holomorphic plane that is associated to this vertex algebra, or is it?
Well, this thing isn't really a vertex algebra anymore, and I'm not sure. So you can construct. You can construct sort of the denominator function for this BKM algebra by starting with a vertex algebra and then doing some kind of BRST reduction, but then what you end up with is not really vertex algebra anymore. And as far as I know, I don't really know the history very well, but as far as I know, this was this formula came from kind of a guess by considering certain degeneration limits of this Siegel upper half space and matching with degeneracies of BPS states in particular limits. Maybe some of the other people
yes,
know more.
It was a guess. This is Greg. Yes, it was a guess. Yeah. And there are people I've heard talks from Eric Verlinde, and there's also a paper by Davide Gaiato, I think, which tries to interpret this omega as a gene, it's the period matrix of a genus 2 Riemann surface, and the idea is somehow you come from the 2-0 theory in 6 dimensions, compactifying on a 2-0 theory, compactifying on a genus 2 curve to get BPS states. I've never been terribly convinced by those talks, but anyway, there are proposals of that nature.
Yeah, thanks. So I think the root of your question. Oh, sorry.
Yeah.
Go ahead.
No. So aside from this genus 2 thing, so in this formula, sigma tau and z, are they related to moduli of like K3 times C2, or are they just sort of abstract?
They're kind of chemical potentials for these charge invariants, which I didn't write down, but like P squared, Q squared, P dot Q, things like that. So I think the interpretation of the genus 2 surface is still not resolved, I guess, or not fully understood. Yeah, thanks. Okay, so I want to talk briefly about, give you a little bit more detail about constructing BKM algebras and superalgebras, and briefly mention some examples beyond the monster-Lie algebra that will then try to reinterpret as playing a role in asymmetries of BPS states and certain string compactifications. So the way you construct a BKM algebra or superalgebra in a little bit more detail than I said before is you start with a chiral vertex operator algebra or super vertex operator algebra, which I'll call V. If it's bosonic, then you can start with central charge 24 for our purposes. And if it's fermionic, you start with central charge 12. And you can construct an associated BKM algebra, which I'll call frac G, via a very familiar technique in string theory called a BRST reduction. So what you're doing is you start with a chiral world sheet theory, which is given by V tensor, this vertex operator algebra for this lattice gamma 1, 1, tensor some ghost particles. You perform what string theorists call a GSO projection on this chiral world sheet theory. And then you consider the cohomology of the states in the theory with respect to some nilpotent supercharged Q. And by considering this cohomology of Q, you define a Hilbert space of physical states. And then you prove that this Hilbert space has the structure of a BKM algebra or superalgebra, depending on whether you started with something bosonic or supersymmetric to begin with. And in order to prove this, the basic method is that you check that this physical Hilbert space satisfies a list of properties which characterize the BKM algebra. And so this is a nice construction inspired by physics, but it has some caveats, which is that you start with a world sheet theory, which is chiral, and you end up with a theory, and then you compactify additionally on this lattice gamma 1, 1. So in essence, you're compactifying all space-time dimensions, starting with a chiral theory. So these are not the kind of string compactifications we usually like to consider when we do physics. But nevertheless, let me talk a little bit about what kinds of vertex operator algebras we can start with. And so I talked about 2 different cases, one where you start with a central charge 24 bosonic theory, and one where you talk about start with a fermionic theory of central charge 12. Now, in the case of C equals 24, they're actually conjectured to be 71 different holomorphic bosonic VOAs of central charge 24, and you could start with any of them. The example that I first talked about was starting with this monster VOA. You could also start with one which is given by bosons compactified on R24 mod one of the Niemeyer lattices, 23 Niemeyer lattices, or just the Leech lattice. So there are 24 more of these, or there's an additional 46 others, I guess, which you could start with. In the fermionic case, there are actually only 3 different theories you could start with, because it was recently proven that there are only 3 unique super vertex operator algebras with central charge 12. One of them is considering chiral bosons on an 8 torus given by R8 mod the E8 lattice plus their fermion superpartners. One is what's called the Conway vertex operator algebra, which appeared earlier. And it's the unique central charge 12 VOA with no fields of conformal weight 1/2. This has some connection to moonshine. It's kind of the supersymmetric analog of the monster module. Or you could just start with 24 free chiral fermions. And if you want to start with a central charge 12 super VOA, then these are kind of the only 3 possibilities you have. And in fact, they're all related. Each of them has quite a lot of symmetry, and they're related to each other by gauging certain discrete symmetries and taking an orbifold. So I want to tell you a little bit more about this VF natural, which I called the Conway VOA. It has a unique choice of n = 1 super current. And if you construct, well, up to isomorphism, and if you construct this supercurrent, you find that this breaks the continuous symmetry group of the theory down to the sporadic group Conway 1. And if you consider the Fourier expansion of its partition function, you find that the Fourier coefficients are precisely equal to representations of this Conway group. And this was originally shown by John Duncan. So this is kind of the natural supersymmetric analog of the observation relating the monster group to the J function. Now we have a function which is half integer graded because we're starting with a super VOA whose coefficients are related to the Conway group. And there's a lot of beautiful mathematical properties that this VOA satisfies, including a version of the genus 0 property for the McKay-Thompson series in this VOA. So one question you could ask, given that this is a very natural generalization of monstrous moonshine, is if there's a corresponding BKM algebra associated with this theory, and perhaps a physical explanation for some of the mathematical properties of this Conway moonshine. And I want to talk about the symmetries of one of the other C = 12 VOAs, which is that of, which I'll call F24, which is a VOA constructed from 24 free fermions. In this case, it also has a n = 1 superconformal structure, which you can define by considering operators which are fermion trilinears. And in fact, you can prove, I think it was done originally by Goddard and Olive, that there are precisely 8 distinct superconformal structures in this theory, which are classified by semi-simple Lie algebras of dimension 24. So these coefficients in this supercurrent, which you write down, precisely have to satisfy defining relations for structure constants of a Lie algebra of dimension 24. And the possible options for these algebras, well, in terms of the affine Kac-Moody algebra, which is generated from the descendants of the 24 fermions, are given here. So each choice of superconformal structure that you write down for this theory will eventually lead to a distinct BKM superalgebra, where these Kac-Moody algebras appear as subalgebras. So there's an analog of Borcherds construction for the monster Lie algebra and a corresponding super BKM algebra derived from the worldsheet theories based on these central charge 12 SVOAs. So I mentioned that there are 3 possible choices. And the first one was the theory of a chiral superstring on R8 mod the E8 lattice, and the corresponding BKM superalgebra was originally constructed by Scheitauer based on this theory. The second one was VF natural, and ignore this comment because I had some additional information in a previous talk about this, but I'm not explaining this here. And the third one is based on F24. So this is just giving references for who originally constructed the BKM superalgebra based on these 3 theories. However, I'm not going to discuss in detail the construction of these algebras here, since the method follows in a very straightforward way from Borcherds' original work, and I want to spend time talking about other aspects of this story. But you can look in papers, 3 different papers for each of these to see more details on that. So this is just sort of repeating the same thing. You can prove that the algebra you get by starting with each of these 3 C=12 theories is a BKM superalgebra. And the method is by verifying a list of properties after doing the BRST reduction to show that the physical Hilbert space satisfies the correct properties for the physical states to form a BKM superalgebra. And furthermore, there's an interesting connection to automorphic forms coming from the denominator formula once you have a BKM superalgebra in hand. So here I have written down sort of all of the technical ingredients which go into this formula for the purpose of the fact that these slides are going to be posted later. But let me just briefly say in words what the connection is. So if you have a superalgebra, you have an even subalgebra and an odd subspace. And so you can divide the roots into either even or odd and compute their multiplicities. And then you can construct a formula very similar to the formula for the J function, which was presented at the beginning, which relates a sum over a Weyl group action to an infinite product, where now you have a contribution from even roots and a contribution from odd roots, one in the numerator and one in the denominator. And in the exponentials are the multiplicities of the corresponding roots. And you can prove, well, Borcherds has proven in a couple different papers that these infinite products form are an automorphic form for a particular type of group, depending on the structure of your data of your algebra. So as kind of an explicit example of what this formula looks like for some of the algebras I mentioned, one can look at the Conway BKM algebra, which is based on starting with the SVOA VF natural. And you can compute the Cartan subalgebra as well as data about the roots. The roots are vectors in a lattice of signature 1, 1, and as well as the positive roots and the simple roots. And all of this data goes into that denominator formula or super denominator formula. And it relates this infinite product here, where these exponents are coefficients of some modular function, to a kind of sum formula, which is a Fourier expansion of this modular form. And now here I have 2 things on the right-hand side. One is a denominator function and one is a super denominator. And that simply relates to whether you compute the contribution of fermions with a plus sign or a minus sign in this infinite product here. So you can define two different automorphic functions coming from a BKM superalgebra. And here you see that the superdenominator for this Conway BKM is a very simple function. It's just 1 over a to the 24th. And you can do this for the F24 theory as well. I won't go through the details. The data, similar data is listed here. And what you find is that there's a similar denominator formula. It doesn't look quite as nice. Here I've just listed the additive side. And the even roots and odd roots are contributions coming from Fourier coefficients of two different modular functions. So this kind of gives you a taste of the relation between modular forms and functions, as well as larger automorphic forms that all are sort of specified by the data of the BKM algebra. Okay, so in the rest of my talk, I'd like to sort of switch gears a little bit and talk about how these algebras can be sort of embedded into certain very special string theory constructions. So our goal is to explore the role of BKM algebras in sort of more realistic string theory constructions, where instead of starting with a chiral worldsheet theory, we have both a holomorphic and an anti-holomorphic sector along the worldsheet, as if we're doing regular type 2 or heterotic string theory. And there are many different models we can consider, where we're going to always take the anti-holomorphic sector W to be one of the three C equals 12 self-dual SVOAs. And for the holomorphic part of the worldsheet theory, we'll either take it to also be one of central charge 12, and this would lead to a type 2 compactification, or a bosonic VOA with central charge 24, which would lead to a heterotic compactification. And all of these worldsheet theories, we want to just be simple factorized theories into left and right, separate left and right VOAs. And so here's a sort of a table of all possible combinations you could possibly make, as well as some of the data of the massless fields in spacetime, as well as their spacetime supersymmetry. So in the first table are the different type 2 models we can form, coming from the fact that we have 3 different C equals 12 VOAs we can play with and compute, and construct factorized worldsheet theories with all possible combinations. This leads to a 2-dimensional spacetime theory with a varying amount of supersymmetry depending on what VOAs you start with on the worldsheet. And then the heterotic models, we can always start with V being one of the 71 C equals 24 VOAs, and then we have 3 different choices for the right moving sector. And again, depending on which VOA you start with, you get a different number of massless fields. Here, capital N tells you the number of currents in the VOA V, the left moving VOA. And the spacetime supersymmetry depends on your choice of the right moving super VOA. And most of these theories, even though we're just describing the worldsheet theory purely in terms of VOAs, they can arise geometrically as asymmetric orbifolds of either type 2 or heterotic string theory on T8, where you take some type of asymmetric orbifold, and then you go to a holomorphically factorized point in the moduli space.
Sarah?
Yeah.
I have a question. So which ones cannot be realized like that?
Well, let's see. These all should be able to, all of the type 2 models I've written down. I think for the heterotic ones, I said most because I'm not familiar with all 71 of the Schelikens series and whether, so certainly the
Okay, I see.
monster
It's one of the
theory,
strange Schelikens theories, then it's
the
not.
Niemeyer series should be able to. I just don't, yeah, I don't know the technical construction of all of them, so I'm not sure about some of the other ones, but if they very well could all be.
Thanks.
Yeah, thank you. So, okay, so now we start with a world sheet theory. Oh, okay, so Jeff says there's now a uniform construction of the 71 Schelikens VOAs. So maybe from that you can determine that they all can arise from asymmetric orbital folds. But so maybe the answer is known, but I don't know it myself. So now we have a list of world sheet theories we want to start with, and we compactify these theories and consider the two-dimensional space-time Hilbert space. And we want to show that there's a BKM algebra which acts on some, at least subsector of physical states in the 2D spacetime. So what we do is we do a similar BRST reduction to what I described earlier for starting with a chiral world sheet theory, but now we have to combine both holomorphic and anti-holomorphic sectors in order to construct a Hilbert space of spacetime BPS states. And what you find when you do this is, well, you start with, again, a no-potent BRST charge, which is the sum of a left-moving and a right-moving BRST charge. And you find that the space of BPS states in spacetime takes the following form. For non-zero momentum, it factorizes into a left-moving tensor, a right-moving Hilbert space, coming from the cohomology of Q left and Q right separately. And then there's you have to do something a little more subtle to consider the zero momentum states. In general, they don't factorize. You can, because you need to consider semi-relative cohomology, and I won't go into too much detail here, but you can see more in our paper. And in defining these BPS states, I've already compactified the spacetime on a spatial circle of radius capital R. And so these conditions and the sum here are coming from the BPS condition in spacetime, which is that these states, BPS states, are annihilated by some right-moving supercharge here, which sets their momenta along space and time to be equal to each other. And in terms of winding and momentum around this spatial circle, you can parameterize these momenta in the following way by integers, little m and n, telling you the winding and momenta of the BPS state. And having constructed this physical Hilbert space of BPS states, one thing that we show in our paper is we prove that there's an action of a BKM algebra or superalgebra, depending on what world sheet theory you start with, on this space of BPS states. So just a little bit more about what this BKM algebra is, what the representation theory of it is. If we start with the world sheet theory, which is V left tensor V right bar, we know from the chiral construction that there's a BKM algebra G associated to V left and a separate BKM algebra G bar associated to V bar right, which has some grading by momenta, and where the state space are related to these cohomology classes of the BRST supercharge. And at non-zero momentum, the BPS states holomorphically factorize into representations where like the left moving part of the BPS state is a state in the BKM algebra G, and the right moving one is in G bar. So roughly the right moving part of the BPS states furnishes n copies of the trivial representation of G bar, where n is the number of right moving supercharges. Whereas the left moving part of the BPS states furnishes an adjoint representation of G. So in terms of the physical states in space-time, it's really just the BKM algebra G associated to the left moving part of the world sheet theory, which acts on the space of BPS states. So for an element in this BKM algebra G, you can construct a representation which acts on these BPS states. I'm just focusing on non-zero momentum here for simplicity. You can also do so for zero momentum with a little more work. And these states are associated with BRST exact states, which live in the right moving NS sector and generate an action of the algebra G on the physical space of physical states in this BPS Hilbert space. And furthermore, you can show that if you consider a correlation function of BPS vertex operators, so if you take n BPS vertex operators, which I'm representing by V sub u here, and integrate over the moduli space of genus 0 surfaces with n punctures, and you act with this representation, the amplitude is preserved. So another thing that we investigate and show is that this BKM algebra G is a symmetry of certain correlation functions of BPS operators in space-time. Another thing that
Sarah, I have a question. Yeah. Aren't those scattering amplitudes a little singular because you're in n+1 dimensions, so you don't have much room to analytically continue in ST and all that?
Yeah, one thing that so we can prove this mathematical formula, but the interpretation is a little unclear to us since we're in 2 dimensions with the we're like on a 2-dimensional cylinder, and these BPS states are like strings, and so I think it's still a little unclear how to interpret these as scattering amplitudes, but as a mathematical formula, it's true. So it gives that a hint that there's some kind of structure here. I'm not sure that I have a great answer to this question, though.
And my recollection is just that kinematics makes you always sit on poles. I could be wrong about that.
Yeah, I mean, you can regulate the integrals such that you can show this identity, but I think the physical interpretation, like even before that, the physical interpretation of scattering amplitude of these BPS states in such low dimensions is really not so clear.
So not to belabor the point, but Jacques was also asking whether the integrals converge, or maybe when you say that it's a mathematical identity, are both sides well-defined functions, or are you proving something about the integrands?
Oh, Yeah, I'm not sure I remember enough of the details to answer very well now.
Sorry.
No, it's a good question. But I don't have a good answer right now. Yeah. Okay. So on a somewhat different topic, we can also sort of make connections to some of the other data of the BKM algebra by considering how the denominator formulas can arise from this physical construction. So we saw earlier that things like data about the positive roots and the simple roots and the vial group of the BKM algebra give you some nice identities which lead to construction of automorphic forms in terms of sum or product representations. And we can try and reproduce that using the physical theory that we've constructed here. So the way to do that is by defining and computing a particular supersymmetric index in the spacetime theory on a spatial circus of radius r, as well as a compactified Euclidean time circle corresponding to an inverse temperature I'll call beta. So we define an index, which I'll call capital Z, by taking a trace in the physical Hilbert space of a -1 to the fermion number in spacetime, e to the minus beta h, some chemical potentials for winding and momenta of the states. And then if there's a spacetime gauge symmetry group, you can also put in chemical potentials for the charges with respect to the spacetime gauge group. So once we've compactified on this spatial circle of radius r, the Hamiltonian can be written in the following way in terms of momentum and winding. And again, these yi are Wilson lines you could add for the spacetime gauge group along the circle if you so choose. And you can show that this type of index is kind of like an elliptic genus, only receives contributions from BPS states. And it's convenient to reorganize some of the parameters in this index. So the momentum, winding, radius, and inverse temperature into two complex parameters, capital T and capital U, which take values in the upper half plane. And they, in particular, they parameterize the Kähler and complex structure of this spacetime torus on which you are computing the index. And so if you reorganize the parameters in this way, the index simply becomes, and then take the note that only BPS states contribute, it becomes a trace only over the BPS sector of the Hilbert space of P to the winding, Q to the momentum, times the chemical potentials, times -1 to the F. And here I've defined these P and Q to be e to the 2 pi I T and e to the 2 pi I U, where there are these new parameters. And this is some kind of signed count of spacetime BPS states. And it should be closely related to either the denominator or superdenominator function for the corresponding BKM algebra G is associated with the left moving part of the worldsheet theory. So I'll give you an example of what kind of function this index reproduces. Say we start with a holomorphically factorized worldsheet theory where the left moving part is a lattice vertex operator algebra based on one of the 24 Niemeyer lattices. 23 Niemeyer lattices or the Leach lattice. So times this VF natural as the right moving part. This is some heterotic compactification to 2D. And if you compute this index, what you find is it takes some infinite product form where these C's are coefficients of the lattice theta function for the corresponding lattice vertex operator algebra. So the data that goes into that has to do with the vectors in whatever the corresponding Niemeyer lattice is. So this lattice, well, the trace in this VOA is given by some lattice theta function divided by eta to the 24th. If you Fourier expand that, you have a bunch of coefficients, C and L's, which appear in this infinite product formula for the space-time index. And you also get a factor of 24 here coming from the fact that VF natural has 24 Ramon ground states. So what you actually find for the index is that it's the 24th power of the product side of the denominator function for the BKM algebra based on this, this lattice VOA coming from this Niemeyer lattice. And something similar will be true in most of our models, as long as they have space-time supersymmetry. So a couple of our models don't have any space-time supersymmetry. So we can't define this supersymmetric index in the same way, but as long as they do, we get something very similar. And maybe you won't get the 24th power, but you'll get some other power depending on what you choose for the right moving part of your world sheet theory. So just as a second example of a type 2 compactification instead, so if the world sheet theory is VF natural tensor V bar F natural, the index that you get is one of two things. You either get 1 over a to the 24th of t or 1 over a to the 24th of u, again raised to the 24th power. And the reason you have two choices is because VF natural has 24 Ramon ground states of weight 1/2. And you can choose what fermion number you would like to assign to them. And depending on whether you assign a plus or a minus sign, they correspond to either BPS states carrying only momentum in spacetime or only winding in spacetime. And that means that the index will depend on either only on T or only on U. And again, you get, if you recall, the super denominator formula for the Conway BKM was 1 over a to the 24th. So what you find again is this spacetime index is precisely the 24th power of the super denominator formula. And you can also get the denominator formula instead by computing some kind of modified index. So instead of inserting -1 to the f, which gives you the super denominator, you can insert just -1 to the f right. So just the right moving fermion number in spacetime, and you'll get a denominator formula instead of a super denominator formula. How much time do I have? I'm almost out of time, right?
Yeah, if you have a few minutes to finish up, that's fine.
Okay, so the last thing I was going to say content-wise was that you could compute this integral via a path integral. So I'm going to sort of skip this part, but I was going to show you that you can compute the same supersymmetric index instead of computing a trace over the Hilbert space in spacetime as a path integral on a Euclidean torus instead. Which connects to the theory of theta lifts in number theory. And you can show that you produce the same index in this way. So you can see that on the slides after the talk if you're interested. So I'd like to just briefly conclude with what I wanted to tell you today. So we've constructed new examples of super BKM algebras and sketched how they may arise in string compactifications to 2 dimensions, at least when the world sheet theory factorizes into a left moving times a right moving sector. And we show in these theories, well, a few different properties. One is that the spacetime BPS states furnish a representation of the BKM algebra associated to the left moving part, that the BKM algebra is a symmetry of certain amplitudes of BPS operators, that a space-time index reproduces the denominator or super denominator formula for the algebra and leads to some nice product representation of an automorphic form, as well as, well, I didn't talk about this, but you can also compute the same index via a path integral. So we hope that these systems will be useful for exploring and understanding further the role of BKM algebras or BPS algebras in string theory, at least in some very special contexts. And we expect that these different algebras might have relations among each other in string theory if you consider the action of dualities, given that at the vertex operator algebra level, many of these theories are related to each other via orbifolds. And so you might expect that at the string theory level, there are also dualities which act on these different string constructions relating them, and may also act in a non-trivial way on these BKM algebras which arise. So one example of the kinds of dualities you might want to consider are coming from CHL orbifolds. I'll just mention these things really briefly. And if you don't know what CHL orbifolds are, you can ignore this. An important open question is if we can understand how BKM algebras appear in higher dimensions. I think that's maybe even more interesting than going to 2D. One way to do this is to study our models under certain decompactification limits, or just start directly with higher dimensional string compactifications and try to explicitly construct BKM algebras in those contexts. And it'd be very interesting to understand how this connects with some of the observations made at the very beginning of the talk, which all arose in 4-dimensional string compactifications. And finally, there are interesting automorphic forms arising. I didn't get to say too much about this, coming from the denominator functions of particular examples of BKM algebras. So one example is an automorphic form for this group, which comes from the BKM algebra related to the VOA of 24 free fermions. This automorphic form is closely related to the moduli space of something called the Enriquez-Calabiel threefold if you expand it at one cusp. If you expand this automorphic form at a different cusp, you get a denominator function for a different BKM algebra. And so you could wonder if these expansions are related to some kinds of dualities between two different string theory constructions for the two different BKM algebras which arise at the different cusps of one particular automorphic form, as well as whether it's connected to some interesting geometric structure of this manifold. And there are other similar examples as well. And finally, you could ask if there's anything to say about moonshine, maybe Bethune moonshine or K3. This VF natural has a very closely related VOA, which is related to the elliptic genus of a K3 surface in a construction due to Duncan and McCrane, which is also related to something called Bethune moonshine. So one could ask whether there's any relation between this Conway BKM algebra and Bethune moonshine. And well, I won't say too much more about that since it's just a speculation. But since Bethune moonshine is related to K3 surfaces, you could also ask if there's some kind of duality frame in which the appearance of the Conway BKM algebra involves compactification on a K3 surface. So that's all I'd like to tell you today. Thanks very much for listening, and let me know if you have more questions.
Thanks for the really nice talk. There are already some questions. Jeff?
Sure.
Hi, Sarah.
Hi.
Yeah, this is a question that I think actually goes back to an earlier paper, but I just was hoping maybe you could enlighten me since your talk reminded me of it. So the connection between genus 0 in the monster and this 2D construction, the genus 0 group associated to some element G of the monster has the form of, gamma naught of the order of G plus some Aitken-Lehner involutions. And so I guess what's happening is that the Aitken-Lehner involutions are elements of the T-duality group. Is that right?
Yeah, I think that's the idea.
But I guess my question is, do you get, because they're very special choices of Aitken-Lehner involutions that you add to get genus 0, and are those picked out physically, or do you get all Aitken-Lehner involutions as T-duality, but then somehow only some of them are genus 0? And what about things like there are these ghost elements where there's a genus 0 group, but there's no element of the monster? I'm just like, to what degree does the physics explain the genus 0 groups?
That's a good question. I feel hesitant to answer because this wasn't my work, and so maybe one of my collaborators would be a better person to answer because they wrote that paper. But I think that their idea was, I think they tried to sort of construct these twisted denominator identities, which you can use to basically prove genus 0 just by facts about modular forms by considering CHL models. Where you.
All right, well, I apologize for asking about somebody else's work. That's not really fair. I guess the other question, which is a perennial one, is so these, depending on exactly what construction you're doing, there are a variety of massless moduli fields. And since we're in 2 dimensions or maybe even 0 dimensions, you presumably ought to be looking at things like wave functions on the moduli space, and there will be regions of strong coupling. And so the physics interpretation is kind of difficult. Has any progress been made on really trying to deal with those issues?
Yeah, I think that's a good point, and that's why I was hesitant when talking about the amplitudes as well, about any kind of interpretation. I don't know that there's been much progress on that. I mean, I think all we can do is sort of write down this BPS index and make which is just a well-defined counting of the BPS states, and make connection to the denominator identity. But in terms of this dynamics and fact that we're in 2 dimensions, and I don't think that much progress has been made, let's say.
Okay, thanks.
Yeah.
Thanks. Greg?
Yeah, hi.
Hi.
Sorry. So let's see, I had 2 questions, a question and a comment. The question is, when you went to the theta lifts, you changed your font on the Z. Does that mean it's not exactly the same Z?
Yeah, that was because
you defined a Z before, and then you didn't have time to talk about the theta lifts, but I noticed that the Z changed.
Yeah, that was because
they're not the same then.
Yeah, so this Z, I can't really highlight. This weird Z is non-homomorphic. So in order to
there's an absolute value there. Oh, I see.
Yeah, we have this
of course, because you did a theta lift, but it's the homomorphic square of the straight Z. Is that right?
Yeah.
All right. Okay.
Yeah. That's
Could you go back?
The font.
And so then I had a comment. So you had 1 over eta to 1 over the discriminant to the 24th. Yeah, there. Right. Good. Yeah, that's okay. I'm just going to make an off-the-wall comment. It's probably just completely crazy, but in the theory of topological modular forms, that's a generalized cohomology theory, and it's periodic. Like complex K theory is 2-fold periodic, and real K theory is 8-fold periodic. TMF is 24 squared periodic.
So
And the analog of the bot element is, guess what? The discriminant to the 24th power. And that's the thing that's invertible in TMF. So the comment, if I try to make this at all respectable, the comment is that what you're getting is, I guess, the Witten genus of the bot element in TMF. So which raises the obvious question, you know, maybe maybe some of these vertex operator algebras define interesting elements in TMF. End of comment.
Thank you.
Are there any other questions? Well, given that we're a bit over time, thanks, Sarah, again. And thanks for all the questions and comments from the audience. And I hope everyone continues to have a good summer. And yeah, Sarah, thanks a lot.
Thank you.